Hi everyone, in this video I just wanted to do a quick recap of the power, product, and quotient rules. So for this example, and we have a few to do over here, so we're going to use the general power rule and or the e to the kx rule to find the derivative of each function. So first thing, I always look at each term and see, do I need to rewrite it? And in this case, because I have the fifth root of x, I do need to rewrite that. Why do we rewrite it? Because what is the general power rule? The general power rule says that if you have x to the n, so if your function is x to the n, then the derivative is nx to the n minus 1. So we want to be able to bring the exponent down and then decrease it by 1. So I need to have x to a power. So let's rewrite. So notice I'm not using my derivative notation yet because I'm just rewriting. So this is still f of x, e to the 10x plus x to the 1/5 minus 9. And now I can take the derivative. So the derivative, well, this one is an exponential. So we're going to use the e to the kx rule. So this one says that if f is e to the kx, then the derivative is k times e to the kx. So one way I think of it is you get the exponential back times the derivative of the exponent. And so here, this is going to be 10 times e to the 10x. Right, you get the exponential back, and then times the derivative of 10x is 10. So, or times that constant in front of just the x. Plus, now here, this is x to the 1/5. So it looks like x to the power of n. And we can use the general power rule. So it'll be 1/5, so bring the exponent down, x to the n minus 1. So this will be 1/5 minus 1, minus the derivative of a constant is 0. You can also think of it as this as x to the 0. So when you take the derivative of x to the 0, you bring the 0 down, and then 0 times anything is 0. So you just get 0, and then just rewrite it so that it looks pretty. So I get 10 e to the 10x plus, well, what's 1/5 minus 1? So this is going to be minus 5/5, so negative 4/5. So this will be, what's that, 1 over 5x to the 4/5. And that will be our derivative. Now for the next example, very similar, but now we have the fifth root of x on the bottom. So we definitely need to rewrite it. So this is going to look like, so I'm going to rewrite. You don't have to rewrite, but I just like to do that to indicate what I'm doing, right? I'm not taking the derivative yet because it's not ready. So this is x e to the x plus 5 plus 1 over x to the 5th. I already know that x to the, or the fifth root of x is x to the 1/5. So then this is going to be x to the negative 1/5 because that fifth root is on the bottom. So to bring it to the top, I have to give it a negative exponent, minus x plus 1. And now it's ready to take the derivative. So g prime of x, the derivative of e to the x plus 5, there's no constant in front of the x, so that's just the 1. So there's the derivative of x is just 1. So then this is just e to the x plus 5. So we retain everything. And now we bring the exponent down. So minus 1/5 x to the minus 1/5 minus 1. General power rule here, right? So the difference between these two is that this is an exponential. X is in the exponent versus here, x is the base. And then the derivative of negative x is minus 1, and the derivative of plus 1 is 0. And we can rewrite it. So g prime of x will be e to the x plus 5 and minus 1 over, what does this become? So this is negative 1/5 minus 5/5, so that's negative 6/5. So this will be minus 1 over 5x to the 6/5. And you can simplify this if you want to go further, right? 6/5, that's an improper fraction, so you can say 5/5 is 1, so it'll be x times x to the 1/5. So I can still do that. So I will say e to the x plus 5, and then minus 1 over 5, right, 6/5, so that would be x to the 5/5, which is 1 times x to the 1/5, which will be the 5th root of x. Hard to see my 5 there, and then minus 1. And that will be it. So you might be wondering, why didn't the derivative of this 5 go to 0 if the derivative of this plus 1 went to 0, right? That's different because this x plus 5, this plus 5 is in the denominator, it's in the exponent of e. So you can think of this as undoing the property of exponents that say we can add exponents, right? We add exponents when you have the same base. When you multiply the same base, you add exponents. So this is e to the x plus 5. But in taking the derivative of this, right, then you'll have e to the 5. I'm just going to reverse it so that, because this is a constant attached to something with the x. So when I take the derivative of this is just a coefficient. So I'll stay with e to the 5th times the derivative of e to the x is just e to the x. So I'm still left with e to the x plus 5. So that's why the derivative of this 5 doesn't, right? I don't just get e to the x. I still get the entire exponent. The derivative of an exponential, you always get the exponential back. All right, so our next example, h of x is 2x minus 3 quantity squared. We're in the beginning of the chapter with the rules of differentiation, so we haven't learned any fancy rules like the chain rule. That's coming up in 2 more sections, so we cannot use that if you haven't learned it yet. So here, how do I find the derivative of this? We have done the product rule, so I could say 2x minus 3 times 2x minus 3, and I could do the product rule there, or I can just multiply it out. So I can say, rewrite h of x is equal to, multiply this out. So I get 4x squared, what's this? So 4x squared minus 6x minus another 6x, so minus 12x, and then plus 9. And now I can take the derivative. So the derivative will be 8x minus 12. And that's it. So the trick with this one is just multiply it out. And our last example for general power rule is part D over here. K of x is x cubed minus 2x plus 1 divided by the square root of x. So I could be tempted to use the quotient rule, but the quotient rule is kind of a lot, right? It's very involved. So instead, I'm just going to rewrite it, because I have a single denominator on the bottom, so I can say that k of x is x cubed over the square root of x, which is x to the 1/2, minus 2x over x to the 1/2 plus 1 over x to the 1/2. Remember that radicals become rational exponents. So I can do that, and then I can use my properties of exponents to simplify. So when you divide the same basis, you subtract the exponents. So 3 minus 1/2, so 3 is 6/2, so this will be x to the 5/2 minus 2x to the 1 minus 1/2 is 1/2 plus, and then that's just x to the negative 1/2. And now that I have it as x to the n, right, now that it looks like that, I can use the general power rule. And so k prime of x, sorry, that looks like an r there, it's k, would be, bring the exponent down, so it'll be 5/2 x to the, subtract 1, so x to the 3/2 minus 2 times, bring the exponent down, 2 times 1/2 is 1, times x to the, subtract 1, so 1/2 minus 1 is negative 1/2, and then minus 1/2 x to the, subtract 1, minus 1/2 minus 1 is negative 3/2. And so that's our derivative. And let's simplify it. Right, no negative exponents. So this will be 1 over the square root of x, and then plus 1 over, or sorry, minus 1 over x to the 3/2. Again, 3/2 here is an improper fraction, so you could simplify if you want to write it a little bit different. right? 3/2 is really 1.5. And so you can say then this is 5/2 x times the square root of x. Because 1.5 would be x to the 1 and x to the 1/2, which is the square root. Minus, I already said that one is 1 over the square root of x, minus 1 over, and then this one you can write it also as x times the square root of x. And so that will be our final answer for the derivative of k of x. So let's move on to the product and quotient rule recap. All right, so for the product rule, so the product rule is if I'm taking the derivative of the multiplication of two functions. So if I have f of x times g of x, and I want to take the derivative. So I'm going to use the prime notation here. Now the product rule says that this is f prime of x, so the derivative of the first times the second left alone, and then plus the first left alone times the derivative of the second. So when you have two functions, you end up with the product of the sum of two terms here. So you have one term here and you end up with 2. F prime of x times g of x plus f times g prime. And so the warning that I had here, caution, that I wanted to talk about is that be careful not to say that when you have the product of two functions and you're taking the derivative, that is f prime times g prime. That is not true. So be careful about that. Don't just take the derivative of each function and multiply them together. That is not what the product rule says. So for the example, the first example that I have, that f of x equals x cubed times e to the x, right? The product rule, I'm not going to say 3x squared times e to the x. That is not what that is. So here I'm going to have to use my product rule. So that is my first function. I usually tend to call them first and second instead of f times g, just because the names, right? Like this is f of x. So if I call that f, that seems a little confusing. So the derivative is the derivative of the first. So d dx of x cubed times the second left alone, and then plus the first left alone times the derivative of the second. And so now I can write it out. So derivative of x cubed is 3x squared times e to the x plus x cubed left alone. The derivative of e to the x is just e to the x itself. So that is my derivative. And with product rule, if you see common terms, you can factor them out. I see an e to the x, so I'm going to factor e to the x out. I'll be left with 3x squared plus x cubed. So that is the proper product rule. So again, watch out, be careful not to make the mistake of saying, oh, the derivative of the product is the product of the derivatives. That is not the correct way of doing the product rule. You should be adding things. And so the extended product rule, if I have the product of, say, f times g times h, then the product will be the derivative of the first times the second left alone, the third left alone, plus then the first left alone, and then the derivative of the second. So g prime times h plus f times g times h prime, and so on. If you add 4, then notice that I'm just kind of moving the prime to each function and the other ones are left alone. So that's one quick way of doing multiple product rules. So what about the quotient rule? So for the quotient rule, we take the derivative of a quotient of two functions. So if I have f divided by g, and I'm going to take the derivative, this is the bottom. So I always think of that you have the top function and the bottom function. So it's the bottom times the derivative of the top. And then for the quotient rule, it's really important that we do minus. So bottom times the derivative of the top minus the top left alone times the derivative of the bottom. Now with the product rule, it doesn't matter that you keep them in order because addition is commutative, right? If you do 4 plus 3, that's the same thing as 3 plus 4. But subtraction is not commutative. 4 minus 3 is not the same thing as 3 minus 4. So we have to be really careful here that we keep the order. So it's bottom times the derivative of the top minus the top derivative of the bottom all over the bottom function squared. Another way to think of it is, and when you have the numerator that's high and low, and some of you may have heard this already, so we go low d high, then d indicating the derivatives, low d high minus high d low, and oops, away you go squaring the low. So that's kind of one way to remember the quotient rule. So the important thing is remember that the quotient rule is minus and the order is important. So you always take the derivative of the numerator first. So let's try our quotient rule examples. So let's look at these two. Which one requires the quotient rule and which one does not? So when you look at this one, the first g of x, so quotient rule or no quotient rule? Okay, let me write that down. And so to determine whether you need the quotient rule or not is, can you rewrite it in a way that you don't need the quotient rule? So can you write it in a way that you need, for example, the general power rule or the e to the kx rule or the product rule? And so this one, right, this has more than one term in the denominator, so we can't split it. So I can't say x cubed over x and x cubed over 1. You cannot split a denominator like that. But this one, I can split it. I can say this is x over x cubed plus 1 over x cubed. That I can do as long as I have a single term, like just one term in the denominator, then I can do that. And so this then is just what's that, 1 over x squared plus 1 over x cubed, and then you can continue to rewrite it. Notice I'm not taking the derivative, I don't have primes yet. So this is x to the minus 2 and x to the minus 3. And now I would take the derivative. Minus 2x to the minus 2 minus 1, so minus 3, and then plus a negative 3x to the minus 3 minus 1, so minus 4. So this will be our derivative. Of course, you want to write it nicer without the negative exponents, and you may also even get a common denominator if that's something you want to continue to simplify. Now here I cannot mathematically split this up. If I had more terms here, like if this was x cubed minus 7, for example, I could say x cubed over x plus 1 minus 7 over x plus 1, right? My denominator has to remain the same, because how do I subtract fractions? You have to have the same denominator. So this will be the only way to split those. But be careful to not split up the denominator itself. So here I do need the quotient rule. So this is my top function or my high, and this is my bottom function or the low. So the quotient rule says, so g prime of x will be low, so x plus 1, d high, so the derivative of the numerator, minus, so low d high minus high, so x cubed d low, all over the bottom square, low square. And you simplify, or in this case, actually take the derivative. So the derivative of x cubed is times 3x squared, and then here the x cubed stays the same, and the derivative of x plus 1 is just 1 plus 0, right? The derivative of x is 1, the derivative of 1 is 0, so times 1 all over x plus 1 quantity squared. Now here, same warning, do not cancel those out, right? These are not, you can't cancel them because order of operations is telling you you should do this subtraction first before doing any division with the bottom. So this we have to, if we want to simplify, I would distribute this 3x squared in. So I'm going to have, what's that, 3x cubed plus 3x squared minus x to the third over x plus 1 squared, and then combine like terms. So 2x cubed plus 3x squared. And that may be as far as I can go. Well, I guess I can factor out an x squared from the numerator. So I'll be left with 2x plus 3. but that is as far as I can go. Now remember, we can only cancel stuff with the denominator if I'm multiplying and it's just a single term in the numerator. So here, even though here I'm multiplying, I don't have a single term, I have minus. So if you have minus or plus, you have to do this addition or subtraction first before you can cancel with anything in the denominator. So at this point, we are fully simplifying the numerator to where we have multiplication, but nothing cancels with the denominator. So that's as far as we can go. So then this is our derivative. So this is g prime of x. And so now I could find something like find the equation of the line tangent to the graph of g at, say, x equals 1. So now I can plug in 1 and find the slope. So that is our quotient rule. Let's try another example. All right, so our last example in this recap video. Find the derivative of this function. So at first glance, it looks like a quotient. I have a numerator and I have a denominator, but my question is to you, do we really need the quotient rule? And what would you say? Do we need the quotient rule? No, right? So this, you can rewrite it. Since I have a single term here in the denominator, I can rewrite f of x to be 5x cubed over the fourth root of x. So that's x to the 1/4 minus 2x squared over x to the 1/4 and so on. And then use our properties of exponents to simplify. So it kind of depends, like would you rather use the quotient rule or would you rather rewrite it? Me personally, I prefer to use the general power rule. So whenever I can rewrite problems so that I can use the general power rule, that's what I'm going to do, because I find that way better than trying to do the quotient rule. So here I'm going to simplify. So 3 and 1/4 was the common denominator. So you want to do 3 minus 1/4. So the common denominator will be 4. So 12 minus 1, so it will be 5x to the 11/4 minus, same thing here, you're doing, right, we're dividing the same basis, so when you divide the same basis, you subtract the exponents. So 2 minus 1/4, common denominator is still 4, so 8/4 minus 1/4 is 7/4, so I'm going to have 2x to the 7/4 plus x to the negative 1. Oh, fourth, not half. How did that become a half? Is 1/4. And now that is rewritten and I can use the general power rule, then I take the derivative. So f prime of x will be, what is that? 5 times 11/4, so 55/4 times x to the 11/4 minus 1. And then bring this down, so minus 2 times 7/4. So 2 times 7 is usually 14, so 14/4, x to the 7/4 minus 1, and then minus 1/4, x to the negative 1/4 minus 1. And then just kind of simplify those powers. So our derivative will be 55/4 x to the, so 11/4 minus 4/4. So 11 minus 4, what is that? So it'll be x to the 7/4 minus 14/4. You can reduce that to 7/2. X to the 7/4 minus 1, so x to the 3/4, and then minus 1/4 x to the, what's this, negative 1/4 minus 1, so negative 5/4. So this is now the only one you have to rewrite because that has a negative exponent. So this becomes 55/4 x to the 7/4. That's an improper fraction, so you can rewrite it in the way that we did for some of the other ones earlier that had improper fractions. And then this will be minus 1/4 minus 1 over 4x to the positive 5/4 once we move it to the denominator. So there are some problems here. I wanted to recap. It kind of looks like a quotient rule problem, but you don't really have to use it. You can you'll get the same answer. It might look a little different, but if you evaluated this, for example, like x equals 1, you should get the same answer than if you use the quotient rule to find it. And when to use the quotient rule, right? Versus when you don't have to. So if you can separate the terms by splitting the denominator, and when do you split the denominator? You have to have either a single term or you have to split it so that the whole denominator stays together. So you can't split a denominator, right? I can't say x cubed over x and x cubed over 1. That's not mathematically correct. So be careful about that. And then, so we have our quotient rule and our extended product rule. And so hopefully that kind of helps you recap both of those rules before we move on to trigonometric derivatives.